60 million people victims of acute hunger. Worldwide famine possible. Projected food shortages reach all-time high. Not enough food to go around. Frequent headlines of recent years. But what is food for humans? It's other plants and animals. Not just any plants and animals. Out of the 4 million identifiable plants and animals, only 11 plants and 35 animals are of major importance to man as food. Our complex societies and civilizations have been possible only because of this unique handful of organisms. A list of organisms which includes grains, such as corn, wheat, rice, and barley, roots, such as the potato, and familiar barn animals like the sheep, cow, pig, chicken, goat, and turkey. Why these few animals and plants? Why not others? The answer goes deep into prehistory. Prehistoric man, depending on wild animals and vegetation for food, would never have gotten much beyond a survival culture. Only by shaping a surplus food supply could civilized cultures develop. Historically, this process has depended on the domestication of a few organisms, the control of their breeding and growth to suit man's needs, which finally resulted in surplus food. Literally, in the process of domestication, an organism is transformed into a different creature, one as dependent upon man as man is upon it. Domestication is an invention of people so far back in time that archaeological evidence casts only a dim light on who these people were and what were their motivations. Questions so intriguing because man, in the last 6,000 years, hasn't added a single new plant or animal to his staple diet. Some animals, like the fierce ancestors of the modern cow, were probably kept and domesticated for ceremonial reasons, with use as a food coming later. How strange to think that the invention which made pastoral and agricultural economies possible, which made populous and complex human societies viable, took place without concern for the final outcome. Were our forebears so thorough that they exhausted all the possibilities for domestication? Why not domesticate a new plant or animal? But where would you look for an animal or plant suitable for domestication? From the first stirrings of human culture, man's relation to animals of the sea has been, with a few exceptions, one of a gatherer. For over 1 million years, the tradition of spear, hook, and net has characterized that relationship. But in the 20th century, this began to change. The apparently inexhaustible natural resources of the ocean and freshwater Great Lakes were in fact being exhausted. Both fish and shellfish, being far up on the food pyramid, had accumulated dangerously high levels of pollutants, making them unfit for human consumption. Still, fish are an extremely attractive source of protein, rating second only to the common egg in total food value. Why not domesticate fish? For centuries, the Chinese have practiced fish culture by rearing carp in ponds, perhaps partly domesticating them. In Europe and North America, pond rearing has become an important component in game and commercial fishing by providing huge numbers of fish, such as trout, for restocking dead lakes or overfished waters. In these aerated ponds, fingerlings are raised on artificial feed to various sizes and then released into rivers and lakes. But not all fish farming or aquaculture experiments are in faraway places like China or focus on restocking lakes. Midwesterners, for a long time, have known about a delicacy called yellow perch. On thousands of lakes across Minnesota, Michigan, and Wisconsin, they come by the tens of thousands to angle for a stringer of perch. The yellow perch, growing to a length of approximately 8 inches and a weight of about 3/4 of a pound, is a social fish, swimming in schools of 50 or more individuals. And until recently, the perch had supported a substantial Great Lakes fishery, supplying fillets for fish fries. Then, as supplies dwindled, thought turned to the idea of farming perch to meet the market demand. Could the yellow perch be domesticated? Each spring, on Madison, Wisconsin's Lake Mendota, there is another kind of perch fishing to be found. By definition, domestication means control of reproduction, the building of a domestic strain, and eventually artificial propagation. But the starting point is the wild animal. And just as it was with our Neolithic ancestor, the modern domesticator has to capture the wild animal and contain it in a man-made setting. The life cycle of the yellow perch starts with an egg stage. Shortly after the ice melts, females, swollen with egg masses, head for clean, rocky, or sandy bottoms. There, they release their ribbon-like structures of some 20,000 to 30,000 eggs. The males have already arrived days earlier. Without interlocking mating behavior to guarantee fertilization of the eggs, the yellow perch seem to have adopted the strategy of male concentrations so great that one is bound to be around when a female releases her eggs. So, although the nets each day are stuffed with hundreds of walleye, bass, and perch, after sorting, a successful day is a catch of 5 to 15 female perch, still ripe with their eggs. Now the process of domestication begins. In 1973, scientists of the UW Sea Grant program obtained a small grant to investigate the possibility of building an aquaculture project around the freshwater yellow perch. Operating under the College of Agriculture and Life Science on the UW-Madison campus, the project was viewed initially with great skepticism and less than enthusiastic support at the national level. Aquaculture had come to mean farming of the sea. However, soon a series of rooms in the basement of the old stock pavilion were converted into a makeshift fish culture laboratory. The goal of this program, unlike many pond and coastal projects, is total domestication in completely enclosed breeding and rearing facilities. Critical to an effort at domestication is control of reproduction, the realm of the fish culturist, who is concerned with what happens from generation to generation. How many eggs do you get? How many are fertile? How many actually hatch? When the project started, even though volumes had been written about perch in sports magazines, little of scientific value was known. So information about the physiology, metabolism, and behavior of the perch had to be generated before the work of building a domestic strain of fish could start. Of particular concern were the events and factors that led to successful spawning, the development and release by a female of her ribbon-like egg mass. If the project was to be a success, this would have to occur under artificial, man-made conditions. Working under less than ideal conditions, Terry Kays has accumulated an impressive block of new information about the life cycle of the yellow perch.
Perch are on an annual reproductive rhythm. That is, they spawn only once a year, and we in our system would like to control spawning, have them spawn more than once. Now, fish generally their reproductive rhythms are thought to be controlled by photoperiod and temperature. Has been thought to be the case with perch. Their gonads start to develop in late summer, early autumn. They spawn in spring, and the gonads grow throughout the interim. Now, we have tested various types of photoperiod. Generally, what we've found is that in the late summer, it is in fact decreasing photoperiod that is responsible for the initiation of gonadal development. After initiation, it doesn't seem to make much difference which photoperiod you keep them on. Moderate water temperatures are conducive to development under both conditions, initiation and continued development. Again, in spring, photoperiod and temperature again seem to play a role. However, there is a very strong endogenous factor. That is, this is an annual rhythm, and you cannot really shorten up this reproductive cycle successfully. However, we can maybe throw it out of sequence so that we can have various brood populations in various sequences. Now, in the spring, we can improve spawning predictability by using appropriate photoperiods, appropriate temperatures, and if necessary, certain kinds of hormones and drugs, and all of these, of course, have been substantiated experimentally.
After egg development, the next step is to achieve fertilization. In 1974, Kays came up with a highly successful method of artificial fertilization. Ripe females, distinguished by swollen abdomens, are selected at the time when they're ready to spawn. First, by pressing gently on the side of the fish, the egg ribbon is released. In order to achieve maximum fertilization, the male sperm has to be thoroughly mixed with the egg ribbon. The wet method, in water, facilitates this process, but also hardens the eggs to sperm penetration. Without a liquid, however, mixing becomes a real problem. The answer has been to use a specially prepared saline solution. Then, once again, by pressing gently on the side of a male fish, the melt, or sperm, is forced into the mixing bowl and stirred around with the ribbon, achieving upwards of 95% fertilization. Both in the wild and in the laboratory, the mixing process has less than 5 minutes to take place. Once fertilized, the ribbons are water hardened in incubation trays for 6 to 7 hours. After water hardening and stretching, so that the ribbon doesn't accordion back on itself, 1-inch samples are cut for controlled embryological studies. On the average, a ribbon may consist of around 25,000 eggs. However, one ribbon was found to be 7 feet long, and it contained over 90,000 eggs. One of the project's discoveries was that the eggs were not, as previously thought, encased in some sort of envelope or held together by a gelatinous matrix, but that the ribbon consists entirely of eggs. This meant, of course, that any tearing or breaking of the ribbon was actually a rupturing of eggs. In order to study the changes that take place as the eggs develop, special incubation baskets and trays had to be designed so that samples could be identified and one could have reasonable assurance that they were all experiencing similar conditions. Accounts of the fertility success of different fertilization methods are kept every day by examining the samples under a microscope. From the moment of fertilization, the perch egg develops remarkably fast, hatching out 8 to 10 days later. Nearly transparent at first, the embryo quickly passes through the neural keel and tail bud stages until the first pigmentation shows up as 2 rather large eyes. From the engineering standpoint, the incubation of perch eggs presents considerable problems. First, fresh water has to be continually passed over the eggs, but circulation currents may trap the ribbon against drains or sides. Second, the ribbon has to be agitated to help the fry escape from the eggs, but too much agitation will rupture the eggs before they hatch. One solution is to go to incubation in outdoor ponds. Here, the natural movement of water would take care of the engineering problem presented by laboratory incubated eggs. In 1976, the university built 2 ponds to test the possibility of outdoor incubation.
Perch eggs are in this rather unique ribbon, and because of this, there are some rather unique problems in incubating them. We're not happy with any of the currently available incubators, and we're kind of in the process of working on this problem and developing an incubator that will work for perch. In the past, perch eggs have been propagated simply by allowing broodstock to spawn in tanks or in ponds and so forth, and putting the ribbons out into ponds and letting them hatch more or less naturally. But this has always been in a low-intensity sort of system. Now we're talking about a high-intensity system, and with this system, we would like to develop stocks of fish that you might say fit the system, and this calls for selective breeding. And with a pond type of propagation, you're kind of eliminating this possibility. So we'd like to be able to control spawning and fertilization and, again, know exactly what eggs come from what parent broodstock and so forth, so that we can get the very optimum type of fish to fit our particular aquaculture system.
But control of reproduction takes you only halfway towards domestication. Rearing or growing out the animals is equally important. In 1975, on the outskirts of Madison, a building was secured for an experimental fish farm. The challenge was to design an economical rearing system which would grow out large numbers of yellow perch. It has 6 parts: the building, rearing tanks, a source of water, a water treatment facility, a source of food, and a method for controlling temperature and lighting. Each had to be integrated to produce a no-stress, healthy environment. For instance, the building mustn't permit penetration of external light. Perch growth rate is highly affected by light. It's been discovered that perch grow best under 16 hours of low-intensity light and 8 hours of darkness. Basic to the whole operation is a good source of water. However, continual replacement of water is uneconomical. Methods for recycling had to be found. First, particulate matter, such as fish feces, is removed by passing the water through a settling tank and sand filters. The most difficult problem associated with reconditioning water in which fish live results from their excretion of ammonia, since ammonia buildup in water quickly becomes lethal to fish. The ingenious solution was a biological filter. Water laden with ammonia is trickled down over a massive bacteria growing on some medium, such as the corrugated plastic sheets used at the experimental farm. The bacteria, in the process of cellular growth, transforms the ammonia into ammonium nitrate, a relatively harmless substance to fish. The result is the filter and fish become one interlocked system. After moving through the filters, the water is returned to the tanks, passing through a mixing valve which regulates water temperature. Perch have been found to achieve maximum growth rates at a constant temperature of 72 degrees Fahrenheit. When it comes to food, there are 2 considerations: the feeding rate and the makeup of the food itself. Obviously, to hand-throw food into the tanks is highly inefficient. It's better to automatically control the feeding rate by some sort of clock. At the fish farm, they've been experimenting with a number of devices that drop a steady supply of pellets into the tanks at preset intervals throughout the day. Even the manufacture of the pellets presents challenges, since a pellet must be durable enough to stand up through handling and submersion in water, yet break down when ingested by the fish. Also, each pellet should contain all the feed ingredients. In the animal world, fish are the most efficient converters of food into body material. However, at present, the exact nutritional requirements are still being explored in dietary studies at the farm. But in general, one can say the problems associated with rearing perch have been solved. Still, there remained one problem. Here's Tom Kaczynski.
For any commercial system, the supply of young animals available to raise is very important. Among domestic stock animals, like cattle and hogs, after the young are weaned, they eat conventional adult foods. Cold-blooded animals like fishes, however, go through several larval stages in which there are changes in their diet. In a natural system, many of these little fishes hatch out. If they don't feed in 4 or 5 days, death follows, of course. In laboratory experiments feeding these tiny little fry, we have been unsuccessful in raising any on artificial feeds because we simply don't understand their nutritional requirements. Recently, we have had good success on a small scale by concentrating the natural foods in very high densities and literally bathing these fry in them, and they have grown out naturally and well. Now, research will be required to understand how these fry select food and what triggers the behavior that initiates feeding. Success in this area is critical if we're to supply adequate numbers of fingerlings for commercial fish production.
It's not accidental that the Perch Aquaculture Project is located at the University of Wisconsin. For in the days of good commercial fish production, Wisconsin consumed approximately 25 million pounds of lake perch per year. In the state, the tradition of the Friday fish fry has risen to such proportions that for most restaurants, Friday has become the most profitable day of the week. From the corner bar to the classiest restaurants, they've all capitalized on the Friday fish fry. So it's not surprising that the fish marketing system reacted with alarm when yellow perch, the backbone of the Friday fish fry, all but disappeared as the natural harvest collapsed. It occurred at a time when, for health reasons, namely low fat and cholesterol, Americans were increasing their consumption of fish, and fish marketeers were looking at what they thought was a bright future for market expansion of the perch and Friday fish fry. Now, instead, fish processors are operating below capacity.
Years ago, perhaps 10 years or so, we were receiving large quantities of perch from many areas, including Lake Michigan. The Lake Michigan production at that time was probably 10 times what it is now. We ourselves could handle in the neighborhood of 500,000 pounds of perch a year through our own processing. If the price of perch were a little less than it is now, we find there is consumer price resistance because of the high price of perch. We also find that competing products such as ocean fish and sauger pike have taken the place in many of the markets. Their price being lower than the perch, of course, it's caused our perch sales to drop to perhaps 10% of what it was. We get perch in from areas all over the United States and wherever it's produced in the United States, plus in Canada. Lake Winnipeg and Red Lake, Minnesota, and the Minnesota lakes, Lake Erie, South Shore, which is the United States, North Shore, which is Canada, Lake Michigan, where the production has gone to a very low ebb, and it doesn't look as though there will be too much being produced in the next few years. So we have to look for other sources of perch. I would venture to say that if the price of perch were perhaps 20 cents a pound less on a producing level, we would be able to market many more pounds of perch than we're doing now.
Fish marketing is such a complex process that a team of economists was brought to the project to analyze the profitability of fish farming. Based on a 50,000 pound per year rearing facility, a ma and pa operation, the initial capital investment was calculated at around $57,000. Including the main operational parameter, the price of fingerlings, the price of food, and the cost of energy to heat the water, they projected a total cost to raise a pound of perch from 89 cents to $1.07 per pound, figures which stand up well against current wholesale prices. There are also less tangible factors in favor of farm-raised perch. An operation patterned after the experimental fish farm can grow out a perch in 45 weeks, compared to 3 to 4 years in the wild. The farm fish is clean, and the retailer can guarantee customers a uniform quality product. And because fish are cold-blooded, they can be held at low temperatures, suspended, without feeding. Once a solid supply of fingerlings, a genetically superior broodstock is available, Harold E. Kelpert, director of the Aquaculture Project, sees a major new food industry emerging and eagerly looks to the future.
We see our research program in aquaculture in the next few years being directed to what we call genetic selection. Up to this point, we've been working with wild fish, but we feel by selecting fish that we have grown and their progeny that we'll be able to get a species of this type of fish that will be a more efficient food converter, will grow faster, and produce the type of meat that we want to meet our market demands. There will be other types of research going on. It never stops, but we feel that this will be one of the major emphases in the future. We've been asked the question many times, well, will these practices be utilized? We're seeing this happen now. And we envision in the next few years the development of several large commercial fish raising operations. They'll be raising many thousands of pounds of fish a year. But this does not exclude the small operator. We are seeing develop small operations in connection with other phases of farming, where they will raise a few thousand pounds of fish a year in conjunction with their other work, and this will help augment our supply that's so badly needed. We also feel that the research that has been done to date and what we will be doing in the future will have quite an impact on our food supply and in related fields. As each of us know, our world's population is growing quite rapidly, and our food supplies are having a difficult time attempting to keep up. Our harvests from the oceans, while they are becoming more efficient, they're also declining in numbers because of our intensive harvesting. If we are to have fish and related food products to help feed the world in the future, we feel much of this will have to be raised by farming or aquaculture practices.
Like the ancient domesticators, have their modern counterparts started something with consequences far beyond their original intentions? Certainly, the atmosphere surrounding the project is one of a significance greater than merely meeting a shortage in a Midwest market supply. Now, having taken the yellow perch through its life cycle under controlled conditions, what about other fish? Fish better suited for large-scale production, such as the cold water whitefish with its small head and bones. In short, a swimming fillet. In fact, it just may be that a whole new set of animal and plant domestications will be needed to sustain us through the high population and energy-scarce future into which we're moving. Clearly, we can now rethink and control what once happened only by accident.